Hi, everybody.
Hi.
Sorry about no Treat Tuesday today.
It's a shame.
Yeah.
All right.
I blame Sam.
We'll live.
Yeah, I blame Sam too.
No, I'm blaming you, Sam.
No.
Okay, so today we're going to move on with the next method for calculating a volume. It's a little tricky, so we'll go slow. And then if we have any time left at the end, we'll go over some of those volume problems from the other day. Yes, your quizzes are graded. No, the scores aren't online yet. I will put them on there as soon as I get 2 seconds. And then we'll go over those quizzes tomorrow. So before we do this, let's get rid of that mess and draw a picture. What is that a picture of? It's a cylinder.
A square rotated over the axis.
What's the volume of that cylinder? Given, of course, that this would be H and this would be, we're going to use capital R in this case. Okay. Pi r squared H. Beautiful. Technically, that should be a capital H because we're talking about the height of a three-dimensional figure.
And capital R, right?
Okay. Now we're going to make something a little bit more interesting. We're going to take that cylinder and we're going to punch a hole through it. Well, this would be dashed. And when you punch the hole through that cylinder, you get a weird shape. And we'd like to know the volume of that weird shape. So how would I find the volume of the stuff that I have left there? Which is basically a three-dimensional,
Coaster.
yeah,
Or like a
Cozy,
like
like
a
a can
beer
cozy?
mug.
like a can cozy, but the
Without
hole
bottom?
goes, all the way through. Stan, what do you think? Were you raising your hand? Oh, I'm sorry, I thought you. So you don't know how to find the volume of that thing? You don't have to be specific. You could just give me a general description, like how you would go about it, and then we can work out the logistics later.
I'd probably use that formula on the side.
That's a good start.
Thanks.
Patrick?
I would take the volume of the outside one and then subtract the volume of the inside.
Okay, the volume of the inside is actually a hole.
Yeah, but I would like pretend that it was a cylinder.
Okay, so if we knew that this had a radius of lowercase r, what would be the volume of that hole through the big cylinder?
The volume of the hole,
Yeah,
pi r squared h.
good. Let me clean this up. I'm getting sloppy here. This should be capital R, and then this should be pi little r squared h. And you said to find the volume of that thing, you would do what with those two?
I would take the volume of pi capital, the capital R, the big one, and then subtract the little one.
Good, perfect. Okay, so the volume of this solid, which we're going to call a shell, by the way, as he mentioned, is volume of the shell is pi capital R squared h minus pi little r squared h. Okay, so any problems with that before we move on to the meat of the lesson? So that's pretty much a little geometry lesson there. You want to find the volume of something that you don't have a formula for, create your own formula. Now, how does this relate to calculus? Well, we're going to find out in a second. But this is something we're going to use. And notice we can play with this algebraically because they have an h in common, they have a pi in common. We can do all that other stuff. We also have this concept of a capital R and a little r, which we had when we did disks. Okay, we good? Wunderbar. Yes?
Are we gonna relate the two R's? Like, will they have a set
Yes.
relationship? Yeah.
Yep.
Okay.
Okay. So we're going to use the shell method. Now, when does the shell method come up? The shell method comes up in that series of questions that I've been going through with you. When we get to the point when I asked, is the Wow. Is the representative rectangle perpendicular to or parallel to the axis of revolution? Up until this point, the answer has always been is perpendicular. But now this gives us the point of when it's parallel to the axis of revolution. I'll show you a visual picture as opposed to a non-visual picture. That was really a dumb statement, I'm sorry. This is going to be the tricky part. When do you use disk method? When do you use shell method? And after today, we'll have all those little tools in the bag. You just have to figure out which tool you're going to pull out and use. And that's where that series of questions will help work that out. And then, of course, today you should be able to perform CPR. How many people are trained in CPR? Outstanding. That makes me feel better on a daily basis.
Actually, no, I'm not. January 2018 it expired.
Oh, yeah.
So if I collapse, don't let Kevin in.
We're all certified.
Can't hear you.
Is shell method only applicable to the parallel
Yes.
representative rectangle, so you can't do it if it's
Nope.
perpendicular?
The shell method. I just threw that in there. It's all in red. And the center of the screen looks awesome. Should have been bigger font, I think, just to really drive it home. Question?
Yeah, I was just wondering on like the idea of like the yes, no, trying to figure out what to use. Do you first see whether or not it's on the axis and then see if it's perpendicular or
We'll
parallel?
go through it.
Okay.
Yeah, we'll go through that method again, and now that we have all those things in place,
Okay.
we'll be able to work that out. Okay, so let's go back to Sketchpad, and I'll show you for those of you that are visual learners and you'd like to see where these things come about. That won't work, of course, because it never does. Let's see, where do I want to go? I want to hide that. I want to come down here. Revolution. Okay, so where are you at, my little friend? Okay, so this is the one we looked at yesterday or the other day. We had discs, and now we get shells. So you see the representative rectangle is parallel to the axis of revolution. It creates a little distance here. We'll talk about that distance. Hi, Mr. Hammond. And when you spin it, you get that shell. And we already talked about how to find the volume of that shell. And so the process will be to find the volume of that shell and then use the accumulator to add up all those shells. Some of the problems you'll be able to use both ways. You could use it as discs and washers, or you could do it as shells. Others, you'll have to do it a certain way. Okay, but that's where that thing comes about. And we can obviously, from looking at this, we can shrink the width of this little representative rectangle to get it down to a very small distance. And in fact, we'll have it such a small distance that we'll get a value of dx, which is what we're looking for. Okay, don't save that. Come back here. These next couple clicks here are going to take you through the process that we've already done, and that is to find the volume of this shell thing. Okay, so here's a shell. I apologize, but let me explain the R1 and R2. I should have used capital R and lowercase r, but when I did this originally, I used R1 and R2. So R1 is the big radius. You know R1 as capital R. And R2 is what you know from the previous discussion as little r. Then I've got this other little r in here, so this gets a little confusing. R1 is the biggest distance, R2 is the smallest distance, but r is that distance smack dab in the center of that disk. Do you understand what I'm saying? Okay. Also known as an average. So I take the big and the small, if I average them, I'm going to get that middle value. That's what I want to work towards, is that middle value, and I'll show you how we get there. H is the height, delta r is the thickness of the rectangle, and of course, since this is calculus, we want delta r to go to what?
Or 0.
To 0, correct. And it makes no sense to put 0 into the formula, so we're going to use dx or dy, depending on the shape of our shell. What I have for you here is all the algebra associated with that. We just did that. Okay? I just used capital R and lowercase r, but it gets us to the same thing. Notice at the bottom there, I changed this into this. All right? So I didn't do the algebra when we were doing the red and the blue stuff at the beginning. But we got capital R squared minus little r squared. That's the difference of perfect squares, so it can be factored this way. Then I pulled this puppy aside and said, if I take the average of those two values, I'll get that middle value that I want, R. I can't just randomly stick a 1/2 in there, so I stuck a 2 in there. After that process, and you're not going to have to do this, I just thought it was important that you see where this comes from, you end up with this guy. There we go. I changed the variables to words because I think the words will help you better when you're setting up these problems. 2 pi h average radius. Average radius is that distance out to the representative rectangle. Since our representative rectangle is going to be really, really skinny, we just want that distance away from the axis. This is the area of the rectangle. The area of the rectangle is what we've already done. The height of the rectangle times the width. The width is dx or dy, depending on which way we're working. And you can already see where the problems are going to come about. First problem, when you use shells, you've got a 2 pi. When you use discs and washers, you have only pi. Area of the rectangle is still the same. You guys hear crackling of plastic, so you think somebody has treats, so everybody burning up like meerkats. Somebody's got food?
And he starts
I thought they were going to attack you, Alex.
He
He's got food, get him!
No, start putting it in his backpack as soon as Mr. Reedy comes in this area, because everyone starts looking at Mr. Reedy, and then they're eyes are glancing out for their food.
I wouldn't do that to you.
Attack it.
Okay, so eventually we get down to this puppy, which looks very different than the disc and washer formula, but it's just close enough to cause some problems. Again, disc and washers have a pi out in front. Shells have a 2 pi.
Oh my.
Disc and washers are r squared dx. Shells are x, f of x dx. What the heck is the x, f of x dx? Well, x is the distance away from the axis. So when you draw your representative rectangle, you're going to have to calculate how far is that rectangle from the axis of revolution. Sometimes it'll be real nice. In fact, the first example, it's easy to figure out. What's f of x dx? F of x dx is what we kind of know as the area of the rectangle. How tall is the rectangle times how wide is the rectangle? Okay, tall is the function, width is the dx, real skinny. And then obviously A and B is how many rectangles we have going from where to where. So building shells.
So f of x is just going to be, it's just going to be the function, right?
Yeah. Sometimes that function, however, you'll have to get a top minus bottom involved or a right minus left. It, you know,
Once you get, yeah, for the.
we're going to crawl first and then we're going to run.
Yeah.
So, big jump. So let's crawl first. Are we good? By the way, these should, if you haven't already figured it out, these are note card worthy. You know, shells, discs and washers, that kind of stuff. Okay, so here's this weird function, whatever it is. There's my representative rectangle, and you notice the representative rectangle is big and honking, but that's okay, so you can see it. It wouldn't, if I spun a rectangle of 0 width, you wouldn't see anything. And then you spin that thing around the axis of revolution. X is our distance from the axis of revolution to the center of the rectangle. That was little r in the previous picture. F of x is the height of that rectangle. Dx is the width of that rectangle. Put all that stuff together, you're going to end up finding the volume of that red shell. That's the hard part. Then we use calculus and the accumulator to add up all those shells. Okay, and again, like we've talked about, as you move out, the shells will get smaller. As you move in, the shells will get bigger, only because of the shape of this function. Is the concept okay? Are we good? All right, good. Let's see it in motion. Before I click on this and show you what the picture looks like, because many of you struggled on the quiz yesterday with simple graphing things, I don't mean to make anybody upset, but at this stage, you should be able to graph a line, kids. That was the biggest problem I saw in the quiz yesterday. Not doing calculus. There were 2 problems. Graphing lines and doing math. Okay? Like adding fractions was a big deal for many of you. So let's start with this guy. Y equals 6x minus x squared. What's that look like? I'm sorry, what?
It looks like.
Hey everybody, it's Mr. Beloff.
Hey, Mr.
Hi, everybody. I mean, doesn't it just look like that? Like y equals 6x minus x squared? I mean,
He is 100% correct. Let me rephrase my question. If I were to take that function and graph it on a Cartesian coordinate plane, what would the graphical representation of that function appear to look like? John? Good. Could you be more specific? Where would that be located? That'll be great on the video, by the way.
I just know that that's what it's like.
How do you know that? How do you know it's an upside down parabola?
Because
Oh yeah.
you can algebraically manipulate that so it's negative x squared plus 6x.
Good.
Negative lead coefficient.
Attaboy. Tells you it
Say
opens up.
Flip over the y-axis.
Tell you it opens upside down.
Yeah.
Good. Okay. Any other ideas? Where is that puppy located? Brennan?
For x.
The center of it would be at 6, 6, right?
Why?
Because that's where, so you start at 1, plugging in numbers at x,
Uh-huh.
and then they're positive, it's positive all the way until you get to 6, and then once you get past 6, it goes back down to negative.
Yes.
Yeah.
So your previous statement is incorrect. Your secondary statement is dead on. So if it starts to go back down, if it becomes negative after 6, what does the parabola look like? Where is the center of that parabola? I heard somebody say it. 3, right. Yeah, so you're right. It's negative, it hits 0. We get positive values, so it's doing something in there. Then it hits 6 and drops back down to 0. So it's symmetric between 0 and 6, which means the vertex is at 3 something or another. Okay, good. I assume you know what that looks like, y equals 0. What's that look like? Okay. What's it also known as?
The x-axis.
X-axis. And we're going to take that and spin it around the y-axis. After all that, we get that picture. So there's our bounded region. Remember, the regions that we spin have to be bounded. It has to be a finite region. We do not have treats today, I apologize.
no, I was just looking at the back of the room.
You could bring us treats.
That was subtle. Right, but so if we pull those two down and then just go from that corner to even the edge of the shelf,
Even if we just turned that other one into a whiteboard, that would, you know, I mean,
it's better than nothing.
right?
Yeah.
I'm allergic to it.
Just don't lick it. Don't lick the tray.
There's a lot of talc.
And then put it in the center of the back.
Right.
Cool.
It's not average.
Yeah.
We just get it on a
Oh, it's
swivel,
flavored.
Yeah.
banana, and it's flat.
Yeah. Either one. I'm okay with that.
Alright, he's done.
See it. Okay. So we have that finite region. If you're doing this problem on a quiz or a test or homework or whatever, you're going to have to go through some self-talk here to figure out what that looks like. Yes, could you pick up your calculator and graph it? Certainly. It's one way to handle it. But let's suppose it shows up on a test on a non-calculator quiz like you had yesterday. You have to be able to put together an idea of what that function looks like. So the blue region is our bounded region that we're going to spin around the y-axis.
Where does the red thing come from?
Yeah, why do we need that?
Well,
that's
I'm
the
getting
rep-
there.
Well, that's the representative, right?
So let's go through the problem. Would you like horizontal or vertical rectangles? Vertical. Now, that doesn't mean you can't do this problem with horizontal rectangles. We could turn this into a washer problem. But why would we do a washer problem here? Here's the issue. If I turn this into a washer problem, I have to solve that function in terms of x. Can you solve that for x? I don't know how to. That's number one. Number two, I'm also going from a function to a function. If I've got a horizontal rectangle here, I'm going to go from the positive side of this function to the negative side of this function. So it creates a whole bunch of problems. So we go with a vertical rectangle, which means we're working in x or y? X. That always holds true. It doesn't matter if you're doing discs and washers or shells. If your rectangle is vertical, you'll be working in terms of x, which is good because I have my function already in terms of x. Is it parallel or perpendicular to the axis of revolution? Parallel, and this is where we divert from the discs and washers. Now it's parallel, that means it's going to be a shell. With a shell, we need two things. We need to know how far is the representative rectangle from the axis of revolution, and we need to know the area of the rectangle. Everything else falls into place. Since I chose to do the first one along the y-axis, it's a little bit easier. How far is this rectangle away from the axis?
Just X.
Just x. We have no idea because I put it here, Ella could have put it here, Olivia could have put it there. It's some number between 0 and 6. How big of a number? Well, x, because we're sliding left and right.
What happens when you've got two functions there, though?
Two functions would require two integrals.
Oh, so like even if they were, well, if it was the area.
No, not two chains.
The area between them, it would still, you'd still need two integrals.
Yep.
To do shell.
Yep. When is this x value going to change? When we're revolving around something that's not the axis. So let's suppose we do the same problem, but we revolve around the line x equals -1. We'll get to that in a second. Okay. How tall is that rectangle? 6 minus x squared. Or 6x minus x squared. Good. How wide is it? dx, because we want a really skinny rectangle. Okay. Now you go back to the formula you copied down from a previous slide. We need a 2 pi out in front. Why 2 pi? Because it's a shell. We're taking rectangles from where to where? Nope. 0 to 6. Good. Again, remember our rectangles are sliding along the x-axis, so we're going from 0 all the way to 6. That's x units away from the axis of revolution, and the area of the rectangle is 6x minus x squared times dx. Put all those puzzle pieces together, and we get that. Okay. So again, 2 pi out in front because we're doing a shell. We're taking shells from 0 to 6. The rectangle over here is x units away from the axis of revolution. There's the height of our rectangle. There's the width of our rectangle. Yes?
If it was, say, the line y equals 1 instead,
Hold on, not yet.
it's not just x minus 1.
Not yet. Right.
Would, like, so in the formula, the x in front of the alpha of x, would they ever like give you a number for x there, or is it always just gonna be?
It won't always be x, but it will always be a variable.
Okay.
Because that's the choice that we make as to where we want to put our representative rectangle.
Okay.
And so pursuing your question more also entails what he's asking. So let's put that on the side burner for a second and finish this. Okay. Everybody good? Any questions so far?
This seems easier than the other one.
Okay.
Well, I mean,
How many think this seems easier?
So far.
Okay, that's
well,
good.
one
So
thing,
far.
it's just,
Alright.
I mean, it seems easy, but it's gonna, I bet it's gonna get harder.
Well, yeah, of course it's gonna get harder. I mean, but it doesn't necessarily have to. Mary, how would you solve that integral? Other than fn int.
Multiply the x out.
Beautiful.
And take
Okay. Well done. Multiply the x out, and then take the integral of 6x squared minus x cubed. Plug your numbers in. Bingity bangity boomity. You're good to go.
They should call multiplying of polynomials the grinder method.
The grinder method?
Yeah.
Oh, the grind.
Cause that is like multiplying out like 10 polynomials, that's a grind.
Okay.
And you have to do that to not do chain rules, so.
Okay. Yeah, I was just gonna say, you beat me to it. I was just gonna say the same thing.
Part of this thing called Pascal's triangle.
Oh, I've got that. Okay, so now, addressing your two questions, what happens if it's not the y-axis? So, two new functions, x squared plus 2, you should know what that looks like, but I've already shown you the picture. The line y equals x plus 4 has a y-intercept of 4 and a slope of 1. But this time, we're going to revolve around this big black line over here on the right. And again, you're tired of hearing this, but I'm going to go through it again. Vertical or horizontal rectangles? Vertical. Are we working in x's or y's? X's, because it's vertical. Is it parallel or perpendicular to the axis of revolution? Parallel. Therefore, we're using a shell. For a shell, we need two things. We need the area of the rectangle. Let's do that first. Christelle, what's the area of this rectangle down here?
It's
How wide is it?
dx.
Good. How tall is it?
X plus 4 minus x squared.
Correct. Top minus bottom. So the top function is the x plus 4. The bottom is that. I should probably stop putting answers to my questions on the screen.
Yeah.
Okay.
Yeah.
So you've got that times dx is the area. How far away from the axis of revolution is that rectangle? In other words, what's this distance? So Brendan, I think this is what you were asking, and Cam, I'm almost sure this is what you were asking.
Yeah.
What if it's not just x? Can it be something other than x?
It's like x plus 4, or is that what it changes into? Or x minus 4?
No.
No.
How do I find that distance?
Oh, function system.
What are the two buzz phrases that we're always using with volume? And area for that matter.
Radius.
Nope.
Top minus bottom.
Right minus left, top minus bottom. Which one is this? Right minus left. What's on the right?
X equals
5. And what's on the left?
X plus 5.
Let's back up. Suppose I was revolving it around the y-axis. How far is that? X. Very good. So therefore, how far is this? 5. So, how long is that? 5 minus x. Very good. So you can think of this rectangle as being at the point x. And therefore, when you do right minus left, you have 5 minus the location of the rectangle, which is x. Now we have everything. Oh, wait, we need one more thing. I'm taking rectangles from where to where? What are my limits of integration? -1 to 2 or 3 to 6? I'm trying not to listen to him. Caitlin, what do you think? Rouse.
3 to 6,
Why?
because it's going around in x equals.
Then why choose the y values?
So -1 to 2.
Right, your answer was correct, you just chose the wrong numbers. Yeah, we're going around the x values, so we want the x coordinates. So -1 to 2. Now I think we have everything. We know our limits of integration. We know we have the distance from the axis of revolution is 5 minus x. We know the area of that rectangle is x plus 4 minus x squared times dx. Put that all together, we're good to go. Are you doing aerobics or you got a question?
Just good. Nothing.
What's the matter?
Why is it x plus 4 minus x squared? Wasn't there x squared plus 2?
Yeah, some seems a little fishy.
Oh, yeah, where's my plus 2?
Confusing me a little bit. That
I don't know what you're talking about, Pat, it's right there.
that makes me feel better inside.
Good, that's why you should ask. Sid, what do you got?
Leave it in parentheses.
Oh, boy.
Yeah, come on.
Good job.
I'm just going to hell in a handbasket here. Hold on.
Just do -2.
Just different problems.
It's different.
Is it a positive or negative 2? I don't know.
Is that better?
Yeah.
Okay, good.
And we know it's gonna be subtracted.
Sid,
I still don't understand why there's an X.
say again.
Why there's an X right there?
Why is this x?
Yeah,
Because doing this problem, I chose to put the rectangle here. You, however, could decide, oh wait, I'm going to put the rectangle here. Or here. Or here. You have an option as to where you want to put it. So wherever you put it, well, there's no numerical answer to it. We just put it somewhere, and that somewhere is this distance x. So it's a generic expression that allows us to put the rectangle anywhere in the region. Okay.
If
Everybody
you-
else good?
If you were to like specifically put your representative rectangle on like the line x equals 1 and would you have to find in the function where it goes along that line, or how?
No, because the idea behind setting up the integral is that
Is
you're
that it takes
taking
care
all
of
the
it.
possible shells, not just one particular, and they will change. By fixing it at a certain location, you're
You only
fixing
get
its
that-
height, its
you only
volume,
get
and
that
everything
one
else.
shell.
For the 5 minus x part, like I understand how we found it, but where would you plug that in?
I'm getting there, hold on, there we go. Okay, so this is 2 pi because it's a shell. Caitlin helped us with this, -1 to 2. This expression in the back end is the area of the rectangle. This is the distance from the axis of revolution. In that generic formula that I gave you that was in the orange rectangle, it's just x. But when that starts to change around a different axis, then you're going to change it.
I can edit that puppy.
Good. What if you didn't have FN in?
The grinder method.
Yeah, the grinder method.
The grinder method, okay, great.
Grind it up.
Just grind that out, there you go.
Grinder method.
Yep.
Chain rule for engine.
Common mistake. Thanks. Well, first you use the product rule for intervals, then you use the chain rule. Common mistake that happens with not only discs and washers, but also shells, is even if you do FN in that, people forget at the end to multiply by the 2 pi. Don't forget there's a 2 pi out in front there that has to be multiplied when everything is said and done. Okay, now you'll notice in all these problems, we have our region either just touching the axis of revolution or way outside the axis of revolution. What we're not going to have to deal with, and something you can keep in mind when you're drawing your picture, the axis of revolution should never pass through the bounded region. In other words, we're not going to do this problem revolving around the y-axis.
What would that look like?
A mess. Because you have volumes within volumes. So when I spin this part, it would overlap into the other part and cause a problem. You can imagine what it would look like. It would look like a cup with a V in the bottom of it. But from a mathematical standpoint, the volume is screwed up because you've got areas that are overlapping. Question?
Wait, sorry, what's the height again versus the?
This should be a +2 on there.
Okay, and then what would be, because like I know the formula is area and then times the distance, but isn't that?
This is the
height?
area of the rectangle. Area rectangle. This is the distance away from the axis.
But isn't that the height right there? Or no? Like right there. Isn't
This?
that the height?
This is the height of the rectangle, yes. Not the distance away from the axis of revolution. This distance is that guy.
Yeah.
This distance is that guy.
Okay, but that's a height. right?
Correct.
You have to multiply by
Area of a
dx.
rectangle.
dx is the width, that's.
Yeah, dx is the width.
Oh, okay.
That little guy. Which is why the dy and dx become so important in this stuff. Unlike the early integrals where we were just, sometimes we, oh yeah, I forgot the dx. Now it really matters because it determines what variable your function is working in. Any other questions before I move on? Cam?
What if you have a non-horizontal or vertical line that you're rotating around? Bad news bears.
We're not going to do it,
Okay.
yeah, so you don't have to worry about it. Everything's horizontal or vertical.
That's good.
Yeah, because otherwise it's a train wreck.
Because then your horizontal or your representative rectangle would have to be at an angle, right?
I don't even want to think about it.
I'm getting
And
lightheaded.
that's a dot. Yeah, I know. It's getting woozy. Okay. Well, how can we change it?
Trig, give us some
Trig would be good. I didn't use trig. I went in the other direction.
Oh, horizontal. instead.
Yeah. Any idea what 2y cubed minus y to the 4th looks like? No. Okay.
A W.
It's not a bad guess.
T.
The reason I chose this is for the same reason I chose the other function. I can't solve this for y. When you see the picture of this graph, it would somewhat appeal to the idea of working in terms of x. I personally like to work in terms of x whenever possible. This problem is going to force you to work in terms of y. It looks like this. And no, I wouldn't expect you to understand or to know what that looks like without it. Well, even a calculator wouldn't help you here.
Oh, looks like a cake.
Yeah, it looks like a
I'm sorry, it looks like what?
sponge cake.
Sponge cake, yeah, that's what it's called.
A bunt cake, I think is what you're looking for. Bunt cake. In German, it would be a bunt cake.
Nothing but cakes.
That place is
I drive
They're
with
so
that place.
good.
Those mini
So
like
expensive.
little chocolate extremes.
All of a sudden, it became a therapy session.
No, carrot cake's not bad.
All right, so everything we need is in the picture on the left. We have the function, we have the representative rectangle. The only difference between this and the last problem we did is that everything's in terms of y now. So, what's the area of the rectangle?
Top minus bottom dy. Or right, yeah, top minus bottom.
No, right minus left.
Can we just do it?
Top minus bottom is dy.
So right minus left.
Yeah, right minus left. So the function is on the right, 2y cubed minus y to the fourth.
But it's just a zero, right?
Yeah, minus 0. Yeah, so it comes out to y. How far is that representative rectangle from the axis of revolution? We're revolving around the x-axis, so how far is that distance? Y, correct. We're taking rectangles from where to where?
0 to 2.
Kev? 0 to 2, very good. Because again, we're sliding in the y direction, so we're going to start at 0 and go all the way up to 2. Therefore, we should be able to put that together into one big honkin' formula. It's a shell, so we got, do we need to go through the questions again, or are we good?
Good.
Anybody want to go through the self-talk here?
Let's go through the self-talk.
Self-talk, okay. Horizontal or vertical rectangles? Horizontal, x or y? Y. Parallel or perpendicular to the axis of revolution? Parallel, therefore it's a shell. Once we know it's a shell, we need the distance away from the axis, we have that. We need the area of the rectangle, we have that. And we put it together then. 0 to 2. The distance away from the axis of revolution is y. The area of that rectangle is 2y cubed minus y to the fourth times dx. Or sorry, ooh, dy. Sam has a question.
You know how the function, like, it's really close to that, like, it touched the x-axis? What if you put your rectangle down there, and then it, like...
Say that again.
What if you put your rectangle down there, so that...
Doesn't matter.
Doesn't matter. It won't make a difference.
We might see some functions where you could put it in such a place that it would appear to touch at that one particular point. But in general, if the majority of the representative rectangles wouldn't touch the axis of revolution, then it's a non-touching. Multiply that out, take the integral of each individual one, 2y to the fourth minus y to the fifth. Plug in 2, plug in 0, multiply by 2 pi, you get your answer. Okay. How we doing? From my experience, the difficulty with this does not come from the fact that you're working in shells. It comes from the fact that you're working with shells having already done discs, having already done washers, and then the compound things, you've also done area. So with area, you know, nothing's squared in area, but now we get into volume and we're squaring the radius. Well, when you have discs and washers, you're squaring the radius. When you have shells, you're squaring both of the radii, R2 minus R1, you know, all this other fun stuff comes up. Okay, so all that, I think that's what we had, isn't it?
Yeah.
Good. All done. Get it?
Oh.
Shell. It says right there, shell.
That's only half
Turtles
shell.
in the
And these are
Half shell.
turtles.
See,
They're
that
half-
I'm
But there's 4 of them, therefore we'd have 2 shells.